Picture this. You're standing in a sprawling, incredibly busy aerospace warehouse right outside LA. You've got hundreds of computers humming along perfectly. But there's this one small cluster of machines that keeps experiencing these mysterious, intermittent network outages. Literally no one could figure it out. They were plugged into the exact same switches as the perfectly functioning PCs. But when they finally decided to trace the cables one by one, a pretty fascinating physical reality popped up. The working PCs, they had cable lengths of around 75 to 90 meters, but that intermittent PC, it was stretched out to 115 meters. Simply because this standard copper cable was pushed just 15 meters past its 100-meter physical specification, the connection just fell apart. And of course, they usually failed at the absolute most stressful part of the day when that bandwidth was needed most.
So it kind of begs the question, right? Why does a simple piece of wire absolutely dictate whether your network survives or crashes? We spend so much of our time obsessing over the invisible stuff, software, IP addresses, data packets, that we honestly forget those digital bits are still totally bound by the unforgiving physical limits of copper attenuation and light. The physical architecture of a cable absolutely matters, and to be honest, knowing how it works is at least half the battle in networking.
Welcome to this explainer on the physical layer. Today, we're going to build your ultimate network administrator's toolkit for troubleshooting physical layer problems. We're going to literally look inside the wires, break down their internal architectures, and decode the exact physical components that make our digital world possible.
All right, let's take a quick look at our roadmap. We'll be hitting the physical network foundation, cable categories and speeds, inside copper cable architectures, device connections and use cases, fiber optics, and finally, power over Ethernet.
Okay, kicking things off with Section 1, the Physical Network Foundation.
Which brings us right into Section 2, cable categories and speeds.
You know, Ethernet categories have evolved so dramatically just to keep up with our totally insatiable demand for bandwidth. Standard twisted pair wiring is the literal bedrock of our local area networks. But remember, every single packet of data eventually has to be converted into an electrical pulse to cross it. If we start down at Category 5, that handles frequencies up to 100 MHz, giving us 100 megabits per second, which we used to call fast Ethernet. But check out how stepping up the physical quality of the cable unlocks these massive jumps in capability. Category 5E handles gigabit speeds, while Category 6 can push 10 gigabits per second, though only for shorter bursts of about 55 meters. Now, as we push into Cat 6A, 7, and all the way up to Cat 8, we're hitting 2 GHz frequencies and a staggering 40 gigabits per second. But did you notice the one constant here? For most of these general categories, that strict 100-meter distance limit remains a hard physical barrier. That is exactly what took down our aerospace warehouse. Exceed that 100 meters and your signal degrades to the point of total failure.
Let's zoom in a bit for Section 3, inside copper cable architectures. When you actually strip back the cable jacket and look closely at the specific copper pins inside, there's a really stark contrast between the two most fundamental Ethernet architectures. Take a look at the straight-through cable on the left. Just like it sounds, the pins align perfectly from one end to the other. Pin 1 connects to pin 1, 2 to 2, 3 to 3, and 6 to 6. So one device transmits on pins 1 and 2, while the other device receives on those exact same pins. Simple, right? But now look at the crossover cable on the right. Here, the transmit and receive pairs physically cross paths inside the cable. Pin 1 actually connects to pin 3, and pin 2 connects over to pin 6.
And this brilliantly illustrates what happens when we demand even more speed on our networks. See, the older 10 and 100 megabit systems only needed to use 2 wire pairs. But when you upgrade to gigabit transmission, like the 1000 base T shown here, you aren't just using 2 pairs anymore. That architecture demands all 4 wire pairs transmitting simultaneously. So in a gigabit crossover cable, you still cross pins 1 to 3 and 2 to 6, but now you also have to physically cross 4 to 7 and 5 to 8. It's a whole lot more complex under the hood.
So how do we apply this? That brings us to Section 4, Device Connections and Use Cases.
Now that you're armed with a solid grasp of those internal architectures, here are the actionable golden rules for your troubleshooting toolkit. You use a straight-through cable when you're connecting unlike devices, say a PC host to a switch or a router to a switch. But if you connect similar devices, like a switch directly to a switch or a PC straight to another PC using a standard cable, they'll both try to transmit on the exact same pins. They're essentially going to be yelling at each other on the same wire, and neither can hear a thing. To fix that, you have to use your crossover cable, which physically crosses those transmit and receive pairs so the devices can communicate seamlessly.
Now, here's a crucial point to remember. Not all RJ45 cables are actually built for Ethernet data traffic. Take a look at this rolled cable architecture. It completely reverses the pins across the board. Pin 1 connects to pin 8, 2 connects to 7, and so on. You absolutely do not use this to pass regular network data. Instead, it's specifically designed to give a PC a serial console configuration connection directly to a router or switch. Think of it as your administrative backdoor key to manage the hardware itself.
Moving right along to Section 5, Fiber Optics.
Okay, but what happens when standard copper just isn't cutting it anymore? When those 100-meter distance limitations cause warehouse outages or you just need mind-blowing speed? We have to ditch electricity entirely and start sending pulses of light. Fiber optic glass has a very specific anatomy. The center is called the core, and that's what actually holds and transmits the light. Surrounding that is the cladding, which basically acts like a cylindrical mirror to confine the light within the core so it doesn't escape. And because it uses light instead of electrical pulses, fiber provides immense speed, and, maybe most importantly, it is completely immune to the electromagnetic interference, or crosstalk, that so heavily plagues our copper cables.
Just to give you a true sense of scale for this tech, a typical single-mode fiber core is just 9 microns wide, sitting inside 125 microns of cladding. To put that into perspective for you, 9 microns is astonishingly tiny. It's literally a fraction of the width of a single human hair, which is about 50 microns. So yeah, we are sending massive amounts of data across entire continents on a strand of glass that is thinner than a piece of your hair. It's pretty wild.
Now, when you're choosing fiber, you generally look at two main types. Multi-mode fiber has a larger core, and it bounces multiple light particles down the glass. Because these particles bounce around and have to be sort of reassembled at the receiving end, it's really best for shorter distances, like inside a local area network. Single-mode fiber, on the other hand, is a bit more expensive. It forces one single tight beam of light straight down a much smaller core. And because the light isn't bouncing around as much, it can span massive distances. We're talking kilometers instead of meters, without losing any signal integrity.
And our final topic, Section 6, Power over Ethernet.
Let's tackle one last physical troubleshooting challenge. Imagine you have to install wireless access points high up in a warehouse ceiling, or maybe you're putting security cameras on an outside wall. It is incredibly inconvenient and super expensive to hire electricians to run standard power outlets to all those remote locations. Well, this is where the sheer elegance of Power over Ethernet, or PoE, comes into play. By following IEEE standards like 802.3AF and 802.38, we can actually use our standard twisted pair copper cables to simultaneously transmit data and deliver electrical power right to those IP phones, access points, and cameras. It's a brilliantly efficient architecture that solves a massive physical deployment headache, all with one single cable.
All right, let's quickly recap our journey today. We've basically built a comprehensive physical layer toolkit. You now know that straight-through cables are your go-to for connecting unlike devices, while crossover cables are strictly for matching similar devices. You've got your rolled cables giving you that crucial administrative console access, and when copper hits its limit at 100 meters, fiber optics step in to give you immense speed, distance, and interference immunity. Finally, when you've got remote devices to power, PoE delivers both the data and the electricity over a single line. It really is fascinating how a purely physical piece of wire, its length, its internal pin structure, completely dictates the digital flow of our information. But it leaves us with a pretty interesting thought to chew on. As fiber optics become cheaper to manufacture and our global bandwidth demands continue to just explode well past 40 gigabits, is the traditional twisted pair copper network cable ultimately destined for extinction? Or will clever engineering just keep finding ways to squeeze even more magic out of those 8 little copper pins? Honestly, it's definitely something to keep an eye on. Thanks so much for joining me on this explainer, and remember, always keep looking closely at the hardware that keeps our world connected.